So even if a topological space is connected, we can still ask, what do we need to take away from it to make it disconnected? And that's what definition 6.19 is about. Let X be a connected topological space. A cut set of X is a subset S of X whose complement is disconnected. Right, so if you take away everything in S, then the resulting part of X is going to be disconnected. And a cut point of X is a special case. It's basically a point such that a set consisting just of that point is a cut set. In other words, if you just take that one point out of X, then then that disconnects capital X. Okay, or we have this language that a cut set or a cut point of X is said to separate X. Okay? Because the X minus S is going to have a separation, right? So it's disconnected. All right, so here's a nice example on a finite set. 6.20a, prove whether or not the set C, which ironically contains just the point B, is a cut set of the connected topological space X, which consists of these 3 points A, B, C, and I've tried to illustrate the topology right here. All right, well, you notice that X is connected because there's no way to sort of find two non-empty disjoint open sets, right? You've got just B there, but we don't have an open set containing just A and C. So yeah, nothing's going to work. All right, well, to figure out if C is a cut set, we have to figure out whether or not its complement is disconnected. We need to determine whether X minus C, which contains just A and C, is disconnected in X. Right? In other words, disconnected in X means disconnected in the subspace topology that inherits from X. So we need to determine whether this subset AC is disconnected in the subspace topology obtained. How do you get the subspace topology? By intersecting the open subsets of X with the subset that we're looking at, A and C, right? So what is this? What do you get by doing this? Well, empty set intersect AC is still the empty set. And if you intersect B with AC, you get the empty set again. If you intersect AB with AC, you get just A. And if you intersect BC with B, you get, if you intersect BC with AC, you get C. And if you intersect the entire set X with AC, you get all of AC. Okay, so there's our subspace topology. And do we have a separation? We do, right? Since the singletons A and C do form a separation of our subset AC, we see that X minus C is disconnected in X, right? And so, by definition, our set C is a cut set of X. Okay? And another way to say that is that the point B is a cut point of X.